So if you have a two-variable function and is local extreme at the point x0, y0 on constraints. So constraint is given by the contour line of another two-variable function, g. So then what you have is these two gradient vector are parallel. Okay, so that's a Lagrange multiplier. So we're going to talk about the gradient and the property of gradient and then look at the Lagrange multiplier in another aspect. So here's two remarks about the gradient. First is that the gradient g or f, gradient of a function at a point is, so since it's two-variable function, it's two-dimensional vector whose coefficient are partial differential, but basically this is the definition. And the second, actually third, so there are three remarks. The second one is that this gradient is the direction at point x0, y0, where function y increases the fastest. So you can go anywhere on x0, y0, but this gradient is the direction where you can increase your value of function the fastest way. So third one is that the gradient is perpendicular to the contour line of the same function. So if I say this, it may be confusing to you. So let me just write more to the contour line f of x y equals to f x0 y0. So I'm going to prove the third one. So when I say xy equals to fx0 y0, I'm not saying xy is x0 y0 because there's more than one point. There could be more than one point where the value of functions are equal, right? So when I say this, I'm taking all the collection, all the points x, y, whose value of function is same as the value of function at x0, y0. So basically, it's a contour line at the level of x0, y0. So let's prove the third one. So what is the contour line? So let's say C is x0, y0, and the contour line is the collection of xy where this is true. And let's call this C, because it could be, mostly, in most cases, it's curve. So let's say I can parameterize my curve C. So if I draw this curve, it could be closed curve or open curve, whatever. But I know that there is somewhere x0, y0, right? Because it's a contour curve at the level of a function value at x0, y0. And I want to take a small part here, just a small part, and parameterize by ct equals to xt, yt. So t, I can take t to be in a small range around 0. So epsilon is just a small number. So it's just a small number. Okay. And then I'm assuming that C0 is x0, y0. So at the time t equals to 0, it's passing our target point, and I want to see the neighbor of that point along the contour line. And let's take a derivative, c prime t, which is x prime t, y prime t. And what I'm going to do is plug in this ct into the value of function. So cf f is a two-variable function. I can take the x and y here. So if I just take xt, yt from this parameterization, which is fct here, it's just a single variable function, right? So I can just simply write ft here. And let's take a derivative. But before we take a derivative, let's see what ft is. So ct here, ct is a part of a contour line. So when you are at the contour line, you have a value function to be constant. And this constant is this value. So basically, if I change my t around 0, I'm always lying on the contour line. My value function is not changing. So it's always c, right? So this function, the composite function, is actually a constant function. So when I take a derivative, f prime t, it's 0 because it's a contour function, because it's a constant function. But let's take a derivative as a composite function. So when I take a derivative of this composite function, it says that this is equal to the multiple of 2 derivative of the composites here. So first you take the derivative of the outside function, and then you take the derivative of inside. So in the outside function, this is 2 to 1 function. So it's 2 by 1 matrix, f of x, f of y, right? And in the parametric function, we have 1 to 2 functions, so it's 1 by 2 matrix, x prime and y prime, right? So when you take the, sorry, I think I made a mistake here. Opposite, sorry. So f of x, f of y, and x prime, y prime here. And then what happens is fx times x prime, fy times y prime. So this, again, when I say this, everything is in terms of t, right? But we take fx as if f is still the function of variable 2, x and y, and then we plug in x and y by xt, yt to make it into a t variable t function. And x prime, y prime, of course, they are function of t. But look at this too. You can rewrite this expression as a vector inner product between 2 vectors, fx, fy, inner product, x prime, y prime. So what is it? The first one is the gradient. It's the gradient of the function, but it's not only at the point x0, y0, it's always the gradient here, because we're not taking the derivative at specific point, taking a derivative at every t. So it's just the gradient at x comma y, but still x comma y is lying on the contour line, because xy is determined by this function, the parametric function. And what is this? So this is c prime t. So let's compare this to, so this is coming from the chain rule, and this is coming from the basic fact about the contour line. And 0 equals to the inner product of 2 vectors. Which mean, what does it mean? This means that this vector and this vector c prime t is perpendicular each other. Okay? So it doesn't have to be always this point, but actually whenever you have a contour line, at every point you take a gradient vector, it is perpendicular to the direction of the movement of the point on the contour line, which is the tangent line. So here, this is the gradient. So let's say this is our specific point, x0, y0, and your c prime t is the instant velocity and direction of instant velocity. So it's a tangent line. And this is your gradient at ct, right? So it always is perpendicular. The gradient is always perpendicular to the contour line. All right, so let's see an example again. So we had an example that find local extreme of fxy equals to x squared y squared on the hyperbolic line, xy equals to 1. And we kind of graph this function, but you can also imagine in a 2-dimensional level what is going on. So here I graph the contour line of G, which is xy. This is xy. And let's see the contour line of the function, the target function. So the level of the target function can always be positive or 0, right? Cannot be negative. So if it's 0, it's just a point on the origin. And when it's positive, it's the radius square. So the contour line is something like this, the circle. This concentric circle. Right? So you have to distinguish these lines, and the concentric circle, because they are not different coming from different function. So each concentric circle gives you the value of the function f, the target function, right? So every point on the one circle, it has the same value of function of f. Now, I want the point on this xy equals to 1 when it has a value of f. So the value of f is small. There's no intersection between the circle and the hyperbolic line, right? It means that the value of this contour line, the level of this contour line is not attained on any of the point on this hyperbolic line. So you need to have a larger value. So getting larger value until you get to where the circle barely touches the hyperbolic line, right? So this point, at these 2 points, it has the value as the level of this contour line as a circle, right? So now you can go a bit larger. If you take a larger value of circle, then you get here, right? So then you have even more intersection here. So in these 4 intersections, you have the value of target function same as the level of this contour line, right? But now let's think about the size of your level. So size of your level was smaller here than here, right? If you increase the level of your target function, of your contour line of your target function, you get larger and larger circle, right? So you want to go for the minimum size of the circle, because the size of the circle is the level of the target function. When it touches this, when it intersects this hyperbolic line. So that's when it barely touches the hyperbolic line. So this is the case when this is the point that you want to search for. So in that case, what does these 2 curves gives? So these 2 curves gives a same tangent line on this intersection point, right? So tangent line of the contour line of function f and the tangent line of the hyperbolic line at the intersection are equal. So if the tangent line are equal, what can you say about the gradient vector by the third remark? Because tangent lines are equal, the gradient for this xy and fxy are perpendicular to the same line, right? So it could have a different direction, but the perpendicularity are the same. So you could have the same direction, but the opposite direction. No matter what that is, they are perpendicular to the same line. Therefore, they must be parallel, right? So that's one way you can prove the Lagrange multiplier, why it works. So local extreme works, or it has a local extreme whenever it barely touches the contour line of the constraints. And then you want to go for that point by solving this equation. Any questions? So even if you don't understand Lagrange multiplier, you have to remember these 3. Okay, just memorize this. Okay, if you don't understand, memorize it. Not for the exam or not for this class, but for your future. You have to know this fact. Okay, because for my understanding, this is the basic core, the core of this all technology. Okay, so I'm going to introduce two types of optimization problem. One is, let me finish erasing this. So I'm going to introduce two optimization problem. One is linear regression and neural network. Okay. So both uses gradient descent. So what is gradient descent means? So this is the method. It's just the method of finding the optimum value of some function. So gradient descent, it works that way. So this is a method of finding local extreme. So first, prepare your function. So your function, x comma y, is the target function. You want to optimize this. So it does. Usually, you can get either local maximum or local minimum. It doesn't matter. If you want the local maximum, then you can set your local minimum, and then if you want to find the maximum, just take the negative sign of this function, you get the maximum. So I'm going to just change the problem finding for local minimum. Okay, so this is your target, and then this is your initial point. And then you iterate the following. So you don't know whether your initial point is given as random. You just pick any number you want. Of course, if you have an idea where the minimum could lie on, then you can choose the sufficiently near point so that the algorithm works efficiently, but it could be just random point. And this has no way have minimum. So you have to iterate your process, updating your point, your coordinate, to get to the local minimum. So your new point, xi plus 1, comma, yi plus 1, is updated by xi, yi plus h times gradient xi, yi. Sorry, minus. Yeah. So h is a step. So h is just a small number, so that if you update your function, if you update your coordinates, you don't want to update too much. So if you update too much, you want to go from here to here. You want to go small sizes, but you don't want to go this way far away, that way far away, that way far away. So you want the direction. You have the direction. You just want to move the small step into that direction, right? So this step is there's no fixed value for how small this number should be. This step must be found by try and error. So if step is too small, you have forever to find the minimum. If it's too big, you don't get the minimum. It's too rough, right? So you have to find the right amount of your step size in order to get the local minimum in a properly. So you see, this is the gradient of your target function. You want to go for the inverse direction, the opposite direction of a gradient, because gradient is the direction where you increase your function. You want to decrease your function. So you want to decrease the function, and you still want to get to the bottom of it. And when you are actually near the local minimum, what happens to this value? The gradient is gradient is a vector whose coordinates are partial differentials of the functions. If it's local minimum, then the partial differentials are 0. We're assuming that function is differentiable everywhere. So when you go for the critical point, we exclude the first two cases. We only go for the case where the partial differentials are both 0. So when xi, yi goes to the near minimum, then this gradient becomes almost a zero vector. So as you iterate this, it will go forever, but eventually there is a stabilizing thing going on. So your x coordinate and y coordinate will be stabilized at some point because the coordinate of this vector will be almost zero. So every time you update your coordinate, it's not going to change that much. So you know when to stop. Okay, so that's a gradient method, gradient descent. And we're going to apply this. So this is very just a strategy, and I'm not giving you any detail here. So I'm going to apply this to these two problems and see how this works. So linear regression. So let's look at the linear regression first. So let's suppose that we have your high school GPA and your DGIST GPA. So I just finished the admissions thing last week. So you can imagine that your high school GPA could be reflected on your DGIST GPA when you get it into the school, right? So in Korea, so high school GPA, it's kind of a ranking. So it's the first rank is the higher, and you have a 9 or something, a 9, right? So your 9 is the lowest rank, and higher better. I mean, the higher rank, the smaller number is the better performance. So DGIST GPA kind of the max at 4.3 and 0. So you could have something like, there's some exception, but kind of reflecting your high school performance, right? So you kind of want to have a nice explanation of your data. So here, each point is a person. So let's say this person is about 2 in high school GPA overall, and when he got into the DGIST, he got 2.0, something like that. And this person had got 2.5, and he got entered into DGIST, and he got something like 3.8, right? So everyone is different, but each point is a person, and we want to have kind of a model that explains this kind of a relation between the high school GPA and DGIST GPA. So if you look at this data as a point, you can kind of draw a line. Maybe this might explain the best of this relationship between two GPAs. And well, I cannot do by hunch, right? I need the strong reason why this is the best, right? I want to find the best fit. Find the best fit, right? So this is the line. I just want the line. So line is just the slope and the y-intercept. So high school GPA is x and DGIST GPA is y. I want the slope and the y-intercept. That's all. So how do I say this is the best? So what do you mean by best? So best means something is lowest, right? So in the gradient descent or any optimization problem, you want the target function, and you want target function to have a minimum value at your best solution. It could be possible maximum, but let's go for the minimum all the time. So there are many ways you can argue that this is best, so which means that there are many kind of target function to make a minimum, but the easiest one is square sum error. So here, let me define a function f, and I'm going to write down the coordinate here. So what I'm going for is, so let's say these data, let's say we have 10 data here. So x0, y0 up to x9, y9. Okay, there are 10 data, which means there are 10 people. 10 people have high school GPA, DGIST GPA, And this is a value. This is not a variable. It's just a value, okay, specific value. I want to find out the difference between the expected GPA and the actual GPA. So this linear function, the y equals mx plus b, if this is the best, then this must best predict the DGIST GPA based on their high school GPA, right? So if someone got high school GPA of xi, then their expected DGIST GPA must be mxi plus b. So this is the always confusing with real and actual. So real value. So it's kind of expected. And then, but there is a actual value. The actual value is what they actually got, right? So this is yi. And this is kind of, so this is actual. And this is an error between the real value and the actual value, right? So when you take the square of that error and then sum it over all the people. Okay? So that's your function. So now, what's the variable of this function? What is the variable? M and B, yes. Why? Is M and B not constant? Yes, xi, y are constant. And there are two reasons. There is no other than m and b, which is variables, because xi and yi are just constant. It's data. So it has to be a function of m and b. And the second reason is we're not fixing m and b. We're going for the best fit, which means that m and b are now changing. So we are going to change m and b to find where we can fit this line into the data the best way, right? So we're going to change the value of m and b. Therefore, m and b must be variable. So this is the function of m and b. So you see, now before I move on to the expansion, you have to understand what it means. So the real means that this has to be the real value if nothing is wrong. So suppose that you have all high school GPA, and if you did the same amount of efforts in the DGIST, that has to be reflected on your DGIST GPA, right? I mean, that's an ideal situation. But someone put up with this DGIST life, or they got some distraction and so on. And someone who didn't do best under high school did more work on DGIST, so they got to boost up your high DGIST GPA. So some kind of thing going on other than high school GPA, high school performance, right? We call this noise. So kind of you see, you listen to music in the radio, you got a noise, right? So instead of the voice, you got a noise from other channel. So that's a noise, something it's added to your the real value. So this is something that has to be done. This is something what has to be out. But because of the noise, because of our situation, this is what actually happened. So this is an error. So let's expand this in terms of n and b. So let's see. So m squared as this. So I'm not going to write down the index above s here. And let's see, we have yi squared as a coefficient here, a constant term. And the b terms, we have 9, so actually 10. 10b squared. And then I'm just expanding the squares of these three summations here. So we have 2 times xi mb and what? 220. I'm looking at these two. 2 times yib, and what else do I have to do? b, y, x, y. Oh, x, oh no, m. Oh yeah, I'm going for m. So multiplying this and this, I get minus 2xi, yi, m. Okay. So do I get all 6? Yeah, I get all 6, right? So let me rename this A, B, C, D, E, F. So if you're looking at my book, the A, B, C, D to F is not the same A, B, C, D I wrote here in the book. And okay, so now this is just MA, M square, and let's see, CB square, DMB plus, let's put minus inside, make sure it's the same direction. So we have E and F, M, and B. Okay. So this is just general type of degree 2 variable polynomial. Okay. What I want is I want to minimum value of this function. I want the point where this function has minimum value. There are two ways. One is using gradient descent. I'm going to show you one other way, which is using Hessian. So what does it say? So it says, oh, okay. So D is the same D, so it might confuse a little bit here. So let me use small letter A to F here, because I don't want to. F is also the same F. So that's okay. So A, B, C, D, E, F. Okay. So A, D, E, F, B. Okay. So what does Hess's method requires us to do? So first of all, you have to go for the double derivative of the first variable. So it was fxx, but here the first variable is m. So we have to go for fmm. Okay? So fmm is 2a. And what is a? It's a square sum. It always has to be positive, right? And then what is d in the Hess's method? D is fmm fbb minus fmb squared, right? So x and y is now replaced by m and b. So this is your D in Hess's method. Fmm, I know what that is, 2a. And what is fbb? We have to go for b squared. It's 2c. And what is fmb? So there's only one fmb here, which is d. So d squared. So let's plug this inside. We have 4 times a, which is xi squared, c, which is just 10, and then minus d, 2 times xi squared, right? And let's see. I think I forgot to mention 1t, 2t. Yes, okay. So, all right. Let's see. I think I forgot something here. So sorry. So let me check if I did the calculation correct. Here we have minus d mb here is. Yes, that's right. And yeah, I think it's right. So we have what? 4 times 10 xi squared minus xi squared. I think I made mistaken somewhere. This is not the right one. So let's see. bb squared here. 10b squared. That's right. X. Oh, is it opposite? That's kind of confusing here. So Hess's method, go for D. You go for let's see. XX. Yeah, that's right. You have XX, YY, XMM, and M square, right? B, FMB here, B square. Where did I make mistake here? It's 10. Oh no, I didn't make mistake. Oh, it's okay. So we have a 10. Yes. So I didn't make mistake here. So now let's look at these two. These things. So I want to make a perfect square. So think about first one. So it's about the sum of squares, right? There are 10 of each, and you want to take off these. So from here, when you take the square of the sum, you get the square of each sum end came out, and it will cancel one each of these sums, right? So it's going to be 9xi squared minus, now it's 2ijxixj. So you see what I'm doing here? So I'm taking away the square of the term square into the square here. And then there are two of each. So when you take x0, x1, there is x1 times x0. So there are always twice of the same thing. So I just take the index always increasing order, not the same, because it's the same, then it's a square already taken out from here, the 10 of them. So and then you have -2. And then you can see what's going on. So if you take one of these pair, I mean xi, xj, then you can take xi squared and take 2xi xj and xj squared, and then you can sum them up. So where xi, xj come from? It came from here, because there are nine of each. So you can use up 9 places of this kind of sum ends. So this is equal to ij xi xj squared. So think about this carefully when you go home. Many people confused about this, but so when you do this, just believe me at this point, when you do this, it's the sum of squares. It's always bigger than 0, right? Unless they are all equal. I mean, cannot be, because if it's all equal, it's lying on a single vertical line. Which is not the case. So it's always bigger than 0. So now, look at this. Our determinant of Hess's method is positive, and our fxx, which is fmm, is positive too. So whenever you find a critical point of this function, it's local minimum. Okay? Remember the table of the Hess's method. It's local minimum. So what do we want? We want to go for the local minimum. So let's find the local minimum. And let's find the critical point. So only need to find the critical point. So when do you get the critical point? Whenever you have 0 partial derivative. So here fm is 2am plus 2, no, not 2, just d, dv, and plus f, right? So fb is 2cb dm plus, okay, so b and b are also confusing here, right? So where does b come from? Where does this b come from? So it's actually come from where? eb, what is this? fm. Oh, this is this b. Okay, so, all right. So we don't need this because we just want the minimum. We don't need the constant factor. So confusing here. B here and E. Okay, E. So we want these to be equal to 0, right? So it's a system of 2 variables, system of equation of 2 variables, and we actually have a nice way of solving this. So first of all, yeah. So it's 2a d 2c, not d, is it d? Yeah, d, and mb equals to minus f minus e. Okay. So if you just have the data, this a, b, c, d up to f, it's just a constant number. So you can see that this is a function of simple b and m. So you can easily find this. So this equation is written as the matrix multiplication here. 2c equals to minus f. So you can get your MB either using the inverse matrix multiplied on left and right, or using this matrix expression. M is given by determinant of minus f minus e d2c and determinant of the thing here, 2a d d2c, and B of this solution satisfying B here is determinant of 2AD minus F minus E, determinant of 2AD D2C. Okay? That's one way you can solve this linear regression problem. Now I'm going to tell you another way of solving this. So by this way, you can find exact number of M and B. Okay, so that's a nice thing to do. This nice thing to try this. And actually, this is the best way you can try, because the gradient descent is kind of approximation method to find the local minimum. But this one, the Hess's method, actually gives the exact minimum, right? So let's try to use the gradient descent this time. So because it's now confusing, let's change our M and B with X and Y. Okay, maybe that's better for you to understand, and also for me. M is X, B is Y. So M is X, B is Y. Okay. So you can see this function now, x comma y, is of this function. Okay. I want to use the gradient method. First, target is set. Okay. The target. So this coefficient is everything of. A coefficient is fully determined by our data xi and yi. So everything is okay. So now take the initial point. So a random point. Okay. So just random point, because at every point it can be possible, but you can start with your vague idea. Maybe the slope must be negative, so maybe x0 must be -1, and y0 you can just eyeballing where the y-intercept could be. And then x0, y0 is your initial point, and iterate this. So whenever you iterate, I plus 1, let's try to write down all the formula here. So you take xi and yi from the previous step, and then times h times the gradient of this function. So what is the gradient? So fx is 2a x, so xi. Then here we have d yi, and then what? X, which is f here. So that's fx at xi yi. Okay. So sorry for confusing again. Where xi, this xi is different from this xi. This is from data. This is our candidate for the local minimum. And what is fy? So you go for the partial derivative again. So c, 2c yi and plus dxi and plus e, right? So every time you set your point as if it's a vector, and then you do a vector addition. So from this vector, you subtract this vector with a multiple of h, and then update your new vector here. And then the next step, you use this one to find your gradient, and then you keep doing it. So we're going to have a coding exercise at the end, because if I just turn on this screen, I'm afraid I might forget changing the screen here. Yeah, so it's recording. Any questions about this, linear regression or descent?
Final equation is the equation of the best fit values.
Final equation is here. I mean, this one you don't know. I mean, you have to just run the process until you find stabilization of these points. So this is M, this is B, the slope and the y-intercept, right? But we don't know what the value could be. Just have to run it. But this method gives you deterministic answer here. Yeah, there are different methods, but it should give the same answer.
How we can choose which one we should use to give it in demo?
Well, in this case, linear regression, you need to go for this because it gives you the exact answer. But I'm saying that you can also apply gradient descent on linear regression. But it's only because this linear regression is two-dimensional. Let's suppose you have linear regression on higher dimension. Maybe the answer is not as simple as this. So you want, yeah, so you can use the gradient descent case. Any other questions? So idea, oh yes. Yeah, it means convergence. So you will see some, the point is converging. If it's not converging, maybe it's because you have too small h and you need more time, or you have too big h, so that it's kind of bouncing back and forth between the big numbers. But if the target function has a local minimum, and if you choose your point, the initial point, so close enough to that minimum point, then it must converge to that minimum point. So in that case, you don't have no update anymore. So what do you mean by update? So it's always changing, but let's say you want to find your minimum coordinate to be accurate up to 5 decimal point. Then you don't see the change of your values of x and y in 5 decimal points no more, then you can just stop. Maybe it's changing in the later digits, but it's not reflected. So you can just simply stop there. Or you can just run, iterate as much as you want and see what the result is. Any other questions? So let's look at the neural network if no questions here. So everyone heard about neural network. Maybe it's so famous, maybe most of us already had experience of making a neural network. So my story is that when this kind of AI thing appears, they had a TensorFlow. I think there is still TensorFlow, but I tried to use the TensorFlow because I heard that TensorFlow is it's kind of more than 10 years ago. So very effective language to use this AI modeling. And I see the TensorFlow, it's so weird. And it says, even if I want to add two variables, I need to use function add. And I didn't understand what's going on. And actually, I didn't understand what is the neural network. I just want to put my hands on and see what happens. And I couldn't. But nowadays, there are many tools. Even if you don't understand what's going on, you can just make your own AI model. But I think it's not that hard to understand the core idea. And even if you just understand the core idea, I think it's enough to just happily use the AI model without any doubt. So here is the situation. How many? 5. There is a 5 circle. You might see this kind of picture many times. Maybe arrows or not. So this circle is called a neuron. So it's input neuron, and this is output neuron. So neuron is not biological neuron, of course. Neuron is a value. Okay? Neuron is a number. Just identify the word meaning neuron equals value, as if modeling or model equals to function. So you want input values and you want output value. So what you want is you want to minimize this output, right? So let's say this is x1, x2, x3, x4, x5. And we want the function that minimize this output value, and this is z. Okay. So z is some kind of function of. So now it's a tricky point. So it's some kind of function of x1 and x5, and also it's governed. So it's a function of x1 and x5. So let's say it this way. So when the values, 5 values are given, you have to determine your function value, z. So what is the simplest way of determining the value of z? So basically, you want to find a function, you want to make a function of x0 to x5, right? So there are infinitely many ways to write a function, but you want to go for the simplest. That's linear function. So you want to go for the linear function of these 5 values, so 5 variables. So if it's linear, you need constant terms too, right? So this is the simplest, and people found out that the simplest works well, and also it's working very efficiently because it's degree 1 polynomial. So we are just using this. And this neural network picture is kind of depicting the situation of this function. So here, every variable have the weight, the coefficient called weight. So weight is written on top of this arrow, okay? Now, if you want to write the constant term here, you put another neuron here and attach to neuron Z. Now, here's the thing. We don't know what the weight is, okay? So weight is not given. The given thing is xi's. The data, input data is given. We want to determine the weight that best fits the output. So it's like a pattern finding. So you have an input and output. We have an answer sheet. You have a problem and answer. But we don't know what's the inner strategy of finding the answer. So suppose we have, let's see, we have, let's say 1, 0, 1, 0, 0, okay? So then the answer is 1. And then the another thing is 0, 1, 1, 0, 0. And the answer was 0. So this was x1, x2, x5, and let's say this is z. So let's say you have several of these. Let's say this is last one, and 1, 0, 0, 1, 0, 1, 1, 0. And let's say you got 1. So there are many, okay? So based on this pattern, I want to find out my function. I want to find if x1, x2, x3, x4, x5 is given, and I want to know how to determine this, the z, right? That's my problem. So this is my function, and this is the neural network that depicts the situation here. So I need to set up my weight of this part, weight of this value that determines the final result here. Okay? So now, what is the variable? Is x1 to x5 variable, or w1 to w5 a variable? W is the variable. So x is not variable, it's the data. Okay? So if I say this is the function, the function is a function of w1 to w5. So if I put some number in wi, then I can map my x1 to x5 to some value z through this neural network, w1, x1 up to w5, x5 plus b. Okay, so I want to find wi. Okay, so how do I do that? I need to minimize something. What should I minimize? I want to minimize my error, right? I want to minimize my error, okay? So here, let's say we have 100 of those, 100. So now I have question, answer, 100 of them. Okay, so there is so if I have one model with some value in W, then I get some result, which is the real result, which I'm expected to be, but the actual result was this, right? So there's difference. So I want to go for so let's say this is x1 vector, and this is x100, okay? So xi vector has 5 elements here. So there are 100 of them. So when I say x1 I, x2I, x3I, x4I, x5I, they are the coefficient of xi vector, okay? Just notation. And what do I want? So let's first take W1 to W5 and then feed it to xi vector, okay? And then let's call this Z1 up to Z100, okay? So this is the actual result, right? The same thing going on in the linear as in the linear regression. This is the actual result, what I'm expecting to be. But the real result, what really happened was Zi. So here, so this is real. The opposite. Sorry. So this was real. This was real, and this is what actually happened. Okay. So this is error difference. So I want the square sum to be minimized. So this is my target function. So I is now from 1 to 100. Okay. So again, what is the variable of this large f? What are the variables? How many variables are there, for example? How many variables are there in this function f? 2? Yeah, so anyone else? How many variables? So let me write down this equation more. So this function is now mapping this one to here. So final formula is this. So we have W1 x1I up to W5 x 5I plus b minus zi square. So there are many variables. It looks like everything is variables, but there are really the variable that we have to consider as a variable of this function. So think about think about the thing that we cannot change and the things that we can change. Can we change x1i? The x1i is the first variable, first coordinate of the i's vector here. Can I change this? No, it's given as a data, right? So it's not changeable. How about W1? Can I change it? Yes, I can change it. So W1, W5, there are 5 variables. Can I change B? What is B? B was just constant term here. I can change B, right? It's not given. I have to find B, the best B, right? And can I change Zi? No, it's already given, right? It's the answer for the I vector. So there are only 6 variables. This function is the function of 6 variables. So multivariable function of the real valued, right? So I want to find the 6-dimensional point which minimize the function f. That's my problem. That's my goal. So how do we do that? We take gradient descent. This gradient descent. So first, just set random wi and b. So let's call it 0 here. And then update what? So let's call it here. W1 I plus 1, W5 I plus 1, bi plus 1 is updated with W1I up to W5I BI minus H times gradient of F at W, same point, X W1I W5I BI. Okay. So what is this gradient? So everything is clear, but this is just the 6-dimensional vector. And what is the gradient here? So look at the gradient formula here. So we just need to take a derivative. So first of all, f w1. So if you take the derivative in terms of w1, what is it? We have a square. So basically, the square term of w1 squared has the coefficient of sum of x1I squared, right? So we have 2x1I squared from I from 1 to 100. That's w1. And there's the degree 1 term, right? Degree 1 term comes from where? No, the degree 1 term comes from square. I think I just used this chain. What is it? The product rule. What is so? So first of all, here, let me do it this way. So I was thinking of expanding this in terms of w1 and then take derivative, but I think that's the worst way of doing this. So just take the derivative, this square, in terms of w1. So we have summation the same, 1 to 100, and then 2 times of everything the same, w1 x1 I, w5 x5 I plus b minus at I, and then derivative of w1 inside. So just w1, it's only w1 here, times x1 I, right? So that's fw1, and I can change this for every j, just changing j here, right? So I got the first 5 coefficient of gradient. And what is FB? So FB, the same thing. Just take a derivative of this. So if I do this, I from 1 to 100, 2 times of same thing, and times 1, right? So there's 1 in the coefficient. So this is FB, right? And whenever I need to find a gradient at this point, I need to plug in that value right here, up to here, and b, and find the coefficient and find the gradient descent. That's everything. Basically, that's everything. That's all. So it's a matter of now how to make it more complicated. Since we don't have much time, maybe I'll just briefly mention this. So let's say you have an image. What is an image? Yeah, pixels. And pixels has a coordinates and a color. The coordinate is a number, but it's just an index, matrix index. So you can put it into one-dimensional large vector. And the color is just a number too. So whenever you see a color in a laser projector or a computer, it's just a combination of the RGB numbers. So basically it's 8-bit color, so it uses 256 number of values for red, blue, and green. So these values can be just represent an image. So if it's an image of 10 by 10 pixel, it has 100 pixel. So 100 pixel has 3 dimension of colors. So if you just use the grayscale, then it's just 1 dimension. And there are 100 pixel. So there are 100 neurons as an input, and each neuron represents the grayscale color. If you want the RGB color for color, then you need 3 more of these sets as another color. And then what you want for the image is finding the pattern. So let's say you see the image of 1, image of 2, image of 3. You want to label it with 1, 2, 3, right? So your output neuron is that 1, 2, and 3, the number. So you have to convert everything into a number in order to use the neural network. So even when you have, let's say, image of a horse, image of a car, then you want to label horse as 0, car as 1, or train as 2, something like that. And then you prepare the problem set and answer set. Problem is your image, answer is the label of that image. And then you set up your equation, you solve it. Solving means that you want the local minimum, where the local minimum occurs, which means that you want the weight, which makes the error, square error, the minimum. So now, if you really want the best result, you can now put more tricks or techniques into it. So first of all, there are many, but first of all, you don't have to go for the square sum. The error could be measured in a different way. But this one has upper hand when you take the partial derivative. So that's why we sometimes, most of the case, we use the square sum. And what else? So the other thing is what I was thinking about. Yeah, so you don't have to go for the entire setup problem at once. So here you have 100, but 100 is not big in compared to the computer speed. Let's say you have 1 million. You want to have 1 million data sets. You cannot go for the 1 million. I mean, you don't want to train the entire set at once. You can just chop your data set into smaller pieces and then train more effectively and efficiently. So that's another way of you can put more trick. And also, yes, I just remembered. Another thing is, like this one, like this situation here. When you make a linear model like this, even if your input neuron is of the range of 0 and 1, because only just 0 and 1, your output could be bigger than 1 or smaller than 1. We don't know. We don't have no control about this, the output result, right? So what we can do is kind of refactor the value of the output that fits into our expected range. So for example, in this case, when I do compute this part as a linear function, I might get like minus 10 to 10 values. So it's very far away from the expected value from 0 and 1. So I can use this function. Let's see. Let me erase this part. One plus, so E means exponential. So let's see, it's a positive, then it's 0, and positive means 1. So it has to be plus set, and minus 0, yes. Okay, so this is sigmoid function. So I'm introducing this function to explain the case when your expected outcome is way outside of your actual range of your data. So what this function looked like if I graph this function is maybe probably seen this much, something like this. So you have z here and sigma z here, something like this. So when z is 0, it's exactly 1 over 2. So, and if z goes infinity, what happens? Exponential infinity is infinity. So it's kind of infinity over infinity. So plus 1 doesn't do anything on the overall value. So it's increasing up to 1. And when z goes to negative infinity, exponential negative infinity is 0. So it goes to 0. So it converts entire real value into the range of 0 and 1. And the more important thing is this is very continuous and also differentiable function. And also it's very easy to take a derivative. So let's take a derivative of this function. what is sigma prime? So this is 1 plus exponential z, exponential is a square here, exponential z, 1 plus exponential z minus exponential z square, right? So we have 1 plus exponential z square and what? Exponential z. Well, why is it so simple? It is simple because it's sigma 1 minus sigma. So you can get the derivative by original value of your sigma. So you don't need to actually recalculate whenever you have a sigma value, because later you don't want the sigma as a single value. You're gonna have a sigma for the same, for all the neurons, all the output neurons. Output neuron could be large if you have several layers of a neural network. But then if you have to compute the exponential every time you take the derivative to find the gradient, it's gonna take a lot of computational time. But this sigmoid function has a nice formula to compute its derivative, so it's very efficient. So anyway, this kind of sigmoid function is used, again, let me emphasize, used to make the range of output into a certain range. So you can scale the output function, this sigmoid function, so that if you want to make the range of output to be 0 or 1, not 0, 1, but let's say 0 to 2, then you can just multiply 2 here, make an adjustment of your range. And this kind of function is called activation. So what was the name? Activation function? Sorry. Not sure about the name. But just if you see this kind of a name in the context of the AI or neural network, you can imagine the sigmoid function as an example. And remember why we need this sigmoid function in our settings here. So that's all. That's the core. So do you guys take a programming class this semester? Or you guys making a neural network these days? I heard that you guys, in a big programming class, that the project is making a neural network from nothing. So maybe it's for the second year. So anyway, I know that there is some project going on later in your other class, but I hope you can just remember the core idea of the neural network. Probably maybe professor teach you again, but in the mathematical settings, you see where our story begins. Our story begins with the derivative, right? The story begins with the partial derivative, and then we went to the gradient. Before we get to the gradient, we had a discussion about the derivative, chain rule, and other contour things, and also Lagrange multiplier. And then we get to the gradient descent, and the neural network is just a simple example to apply gradient descent in the linear model. So the complication is not because of the mathematical idea, it's the technique. Like what kind of function is more efficient, what kind of settings, what kind of variables, what kind of layers, what kind of things going on. But the whole idea is, I'm not saying that everything is based on gradient descent, but the basic material on the neural network based on this idea, simple mathematical idea, right? So I think I'm gonna stop here.